What's going on, everybody? Welcome back to another Granularity Analytics AI tutorial. Today, we are going to talk about generative adversarial neural networks. That's a mouthful, but I kind of want to get back to my coding roots. I kind of want to get back to where we were developing just purely Python code, nothing else. I think I kind of took a tangent on going down the vibe coding route and maybe the different AI applications that are out there. And I feel like I kind of lost track of just the purely coding some cool AI stuff and learning what we can develop programmatically. So we're going to go back to those roots today in developing our own generative adversarial neural networks. Now, what are general adversarial neural networks, aka what's known as GAN or GANs? And according to ChatGPT, when we asked this question, general adversarial networks are digital game of cops and robbers, but with math. Two neural networks are set up to spar with each other. The generator, its job to create fake data, images, sounds, that looks real. Think of it as a forger trying to print counterfeit money, or a forger trying to print counterfeit money. A discriminator, whose job is to spot the fakes. It sees both real data and generated data and learns to decide which is genuine. What are they for? Image generation, art and design, deep fakes, data augmentation, scientific uses. Now, want me to give you a concrete example of walking through how a GAN could be used in medicine or how it gets abused in social media? Yeah, sure. So in medicine, GANs can be used to generate synthetic MRIA scans of brains with tumors and without tumors. For social media, GANs can be used to power or generate videos of politicians saying things they never said, aka deepfakes. So mainly, GANs are used to generate synthetic data from data we might have had in the past. It's either made to use, like we see in this example, of generating different MRI scans or generating different images, creating photorealistic faces of people who don't exist. So it's able to take things that realistically exist, take those images, take those corpus of data, and then spit out something completely novel. Not novel, I shouldn't say, but synthetically novel, and be able for us to use that information. So if you're interested in synthetic data generation, if you're interested in creating kind of artistic images that are new and different, this is a video for you. Please make sure you hit that like button. Please make sure you subscribe. Please make sure you comment and leave feedback. And let's begin on this tutorial. So I already have a few things already hard coded into this, but we're going to kind of go about in making sure that we code in some stuff and add in some things. So first we want to do is obviously install some packages, install some kind of configurations. As you can see here, device equaling CUDA. CUDA, I think, is from NVIDIA. I'm pretty sure. Batch size 128, noise dimension 64, learning rate. Usually this is the learning rate generally that most people put, like a 0002. Beta 1.5, beta 2.999. Epochs, we're going to take this down to maybe 15. I know we don't have a whole lot of time in this video. I don't want to make it too long. Let's do 12 instead. Don't want to make it too long. So we're using PyTorch for this. If you are not familiar with PyTorch, it's something that's hot in the AI or deep learning space right now. PyTorch and TensorFlow. Maybe I might have another video in the future going down what TensorFlow is, but these packages are used mainly in the deep learning and AI training spaces. If you're wanting to go an AI engineering route, TensorFlow, PyTorch is something you should get familiar with ASAP. But let's go over and run these packages real quick. So like I said, we have PyTorch here. NumPy as NP, matplot, blah, blah, blah. And matter of fact, while we're here, actually what I want to do, I am using Google Colab, by the way, if you are not familiar with it. And we want to make sure we change the runtime to a T4 GPU versus the CPU. Reason being, CPUs take way longer, way more processing power. GPUs obviously are very well used in the AI space. Every AI company, you name it, OpenAI, NVIDIA, Google Gemini, Anthropic, Perplexity, they all use GPUs. They're just better at processing AI information, better at driving AI results, all around just better. So CPU, computer processing unit, GPU, graphics processing unit. Remember that. So now that we get to the configurations, we want to run this, like I said, 12 epochs. Then we want to install Torch Vision and import some data sets. So there's already a few data sets that you can import to try out. I believe the one that we're going to do is the MNIST data set. Now, I think a lot of people in the AI space should already be familiar with this data set, but we are going to add the training set here. Training set equals datasets dot or datasets dot MINST, boom, MINS. Actually, you want the MINST, and then we want here, and then we want to do download equals true, train equals true, and then transform equals train augs. So this will load in our data set so that we can use it as we keep going. MINST is, oh, MNI, sorry, MNI, MNI, oops. Now we should be good to go. Also, make sure you learn how to spell. That can help you a lot in your AI development. So as that loads, we are going to talk about how we can make sure or see the images of our synthetic or the real world information we want to use to then generate our synthetic information. So here, train set, we want 9,000. And then we want to show plotting of the image, img, im show image dot squeeze. I think I spelled squeeze right. Squeeze cmap equals gray. And as you can see here, here's our training set for what we want to train our model on. We want, and again, we could take different numbers here. Let's say 6K. That's another random image. Or let's say 4K. Another random image. And these are all numbers, right? So they're just images of numbers that are kind of blurry to see what our generative adversarial neural network will generate, right? Out of this training set of numbers of that are handwritten, basically. So let's try 1,000. Oops. 0. So we want to go back to just as a showcase, just to keep it on. Well, we could take it out and be like, let's try 3,000. 9. So just as a showcase, I wanted to show you guys that of what's in our data set. That way you can explore it and see kind of what you encounter. But these are all handwritten numbers that we want to try and see what if we can train our GAN on these numbers to generate something synthetic, random numbers in a different order, so forth and so on. So once we get that done, and once we see what's in our training set, we then want to load our data set into batches. So how many, well, let me see. We want to know how many images are present in our training set. Training set. Boom. And then we want to do length of training set. And you can see 60,000. is in our data set that we're using to train our GAN model. So from there, we want to kind of start installing some stuff. So we want to install data loader from PyTorch, as well as make grid from PyTorch as well. Again, making a grid of all our synthetic generative information that we're going to be creating. So then we want to do train loader equals data loader, train set, batch size, underscore batch size equals batch size shuffle true, just to make it random. Boom. And then we want to kind of take what's in our train loader set and say print how many images are in our train loader. Question mark. And then we're going to do same thing, lane or len, length, train loader. Boom. So once we have, so as you can see, 469 is within our train loader set. So let's keep going. And now we want to know the size of our grid and what we're using and what we're training with. So data equals train loader images underscore, because we have nothing to pass here, next data inner. Boom. Forgot to include the, there we go. And then print the shape of our images. Images.shape. Cool. So now we know the size. Now we want to show the tensor images that we are dealing with. And we want to plot some of these images from the batch that we're using or that we created in this train. Hold on a sec. In this train loader set. So we want to do definition show, and we want to create a function here. Tensor images. Tensor img images equals 16 size equals 12828. Unflat underscore image equals tensor dot detach dot CPU. Boom. Image underscore grid equals make grid. And I'll have all this code in my GitHub for you guys to use and take and experiment with it. Num images. I should actually enable the autocomplete, but it's okay. Images. Hop out of this, and then do nrow equals 4. plt dot imsho or show image underscore grid dot permutations permute do 1 2 0 images, and PLT dot show. Invalid decimal. Oh yeah, right there. Okay, I think that's supposed to be a comma. Boom. Nice, beautiful. So now that we have our function created, let's use it to view some of these images within our train loader. So show tensor images. We want images, blah, num underscore images. And we want like at least a grid of 16 here to see what's in our train loader and what we're going to use to train our GAN. So we have 1, 2, 3, 4, 1, 2, 3, 4, equating to 16 if you multiply 4 by 4. We have 1, 2, 8, 5, 5, 1, 9, 6, 9, 3, 1, 7, 0, 4, 8, and I think this is 0, I guess. Like I said, these numbers are going to be used for our model to generate something completely synthetic. We're going to use, I think we want to see 12 epochs to train it and see what it can generate novelly, what images it might generate. So now we want to create the discriminator network. So we want to do pip install Torch summary, just to give us the data and information we want when using Torch and its outputs. Import m from Torch summary, import summary. Cannot support Oh, NN, whoops, sorry. Not MM, NN. There we go. Okay, cool. So next, what we want to do is build out the discriminator block. So def get disc block. We want to do in underscore channels, out underscore channels. Oops. Kernel size. Make sure you spell everything correctly. And stride. Now, I'm not going to go through each and every definition of things. Like, for example, I forgot what in channels and out channels were, as well as stride. But kernel size, I think you get the idea if you're familiar with at least software engineering or ML engineering kind of things. But this is us kind of building out, again, like I said, the discriminator block here. Convolution 2D. And then we want in channels underscore in channels, out channels, kernel size, stride, and batch norm 2D out channels nn dot leaky relu. Set this to O.2. Boom. Now we're creating the class discriminator. And with that, it's basically something that's going to be used to separate the real images from the fake ones. So the class discriminator is what we want. Okay, yes, I know. I will utilize it soon. Class discriminator dot nn module here. Boom. Def init self. Boom. And then we're going to do super discriminator self init And then, so I'm going to kind of copy and paste a lot of this because this could take a while. Boom. So this is it going through the checks and determining the real and fake images that are being passed. I want to make sure that all the self blocks line up. Oh, not for. I would have created another definition called forward. Now, main summary of this is that it's just a determinant in having a conclusion into whether or not the image or the data that is expressed is real or fake. This is kind of the final say here. So it's going to be within the discriminator class. And we want it right here. Cool. So now we want to run this. Nice. Now here's where we start generating the summary itself. So we have D equaling discriminator with D to device, and we want the summary of the data it's expressing. D input size equals 12828 summary. And we want to run it. Forward function, blah blah blah. To device, D input. Missing forward function. It's right there. What do you mean? Let me figure this out for a second. I see what happens. It's a matter of indentation. There we go. Make sure it lines up correctly, y'all. Beautiful. Now it should work. Nice. This is good stuff. So let's kind of determine what this is telling us real quick. So I needed ChatGPT's help to kind of decipher these results. Again, like some of this stuff I understand, some of it I don't. So it's always, with AI being in the mix these days, it's always nice to get ChatGPT's help in determining how to kind of decipher and translate these results, and to just understanding what the hell is going on. So conclusive meaning architecture is valid. The layer sequence reduces 28 by 28 images down to a single classification score. It's efficient, only around 65K parameters, fast to train, unlikely to overfit too badly on small data sets. Interpretation. The discriminator is a simple but effective convolutional neural network classifier, aka CNN. It's not meant to be huge. Its job is to just keep pace with the generator in the GAN arms race. In other words, this summary tells you your discriminator is working as designed, compact, properly structured, and ready to learn real versus fake separation. So all that sounds like good news. All that sounds like stuff I want to hear. Hopefully, ChatGPT is treating me right and giving me all the needed information that I want. So now let's create the generator network to generate these images, or generate the synthetic data at least. So we want to go to this real loss versus fake loss. Copy and paste this into here from a past project. Now, with real loss versus fake loss, this will determine so these fake loss and real loss are used to determine in either punishing I put in quotes, the model when it gets things wrong, when it comes to identifying what is generated data or real data. So that's what these two functions are going to be used for when we're training our generative adversarial neural network. And then here we want to put these in place as well. And we want to then, boom, G, blah, 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 and G is not defined. Yes, right here, I forgot. Here, right under, I forgot to put in place the weights that I wanted originally. Okay, so let's put in place the weights. And the weights will go right under our summary here. Right here. Can I? Oh, here. Boom. And then we want to put in our applied weights here that we'll use with our torch logic. What do you mean? I thought I did create. Oh, I know what I didn't do here. I know we're missing. So I missed what we were supposed to create. I think we created the discriminator already. We kind of jumped ahead. Yeah, D for discriminator. And we forgot to create our generator, which is 100% needed. So we got to kind of backtrack a little bit and go create our generator real quick. I'm going to copy and paste the logic here so we can move a little faster versus trying to do it all from scratch. So let's get our, so we have the discriminator block. Here we want to put in place our generative block. Boom. And we want to put in place our class generator. And you can see that I have it labeled G for generator, D for discriminator here. And that's why we're getting the error of, oh, you're missing the G for this. Boom. And as you can see, it generates the same kind of summary. My recommendation, put this summary into ChatGPT, Claude, Google Gemini, whatever LLM you use to kind of get an idea on what entirely this means. Because even I sometimes don't really know exactly what all of it means. It's hard for me to read. AI could definitely help versus you searching through Stack Overflow or going to YouTube. AI can definitely help you decipher this and decode it. So let's keep going and let's go back and run some of this. So now that we have the weights, let's go back. Boom, that works well. Everything kind of flows better now. Boom, boom, and we're good. So let's keep going right after that. And here we're getting closer and closer to where we're actually getting ready to train our model loop to then train to train for our synthetic data. So we are training for 12 epochs. And here is our loop configurations that we're going to put in place. Like I said, this already was a pre-done project in the past. So I'm just going to copy and paste this here. Boom. And now what you'll see is once we hit the enter key, shift enter, depending on the notebook you're using or the ID. Once we hit the shift enter key, right, you'll see where it will begin to start training. And like I said, we're training it for 12 epochs, and you can train it for as long as you want to. You will kind of have to begin to find this sweet spot of what is the optimal amount of training versus what is too little. Like, for example, if you trade it for 50 epochs, sometimes it's doing too much and it kind of becomes noisy versus maybe if you train it for 20, 10, 15, 30 epochs, sometimes that's better for it. So you kind of have to play with it and really try multiple different kind of counts of epochs for you to kind of get a definite number that could possibly help. So we're going to kind of run this, train it for 12, and see what we get. So as you can see, it's loading everything in. At least that first one that we want to see, and then we're going to kind of see what it trains with and how it what it spits out, at least on the opposite side. So again, you want to make sure you have the T4 GPU if you are using Google Colab. If you're using the Databricks free edition, I think it might already run on GPUs. I'm not 100% sure. But I don't know. Check on that and see. Anaconda, I don't think you could choose a GPU. I'm not 100% sure. But Google Colab for right now, Google Colab and Databricks Community Edition, highly recommend to use for all your AI kind of projects and needs. But anyways, we're going to come back. And as you can see, it's already kind of generating this synthetic information, trying to learn. It starts off kind of very blurry, starts off getting kind of more or less, less blurry. And as you can see, it's generating this synthetic information, trying to copy as best as it can and learn how to generate those same grid-like numbers in our own capacity. So we're going to wait a little bit. I'll come back once it's done and we'll conclude. So as you can see, like it didn't do too well in generating images. So we did try with 12 epochs. Maybe we should run it all and try with 20 this time. Let's give it a try. So I did change it to 20 here from the 12 that we had before. And now we're just going to go for 20 and see how long it takes. It's running now. We're going to go for 20, see how long it takes, and come back with the results to see if it's actually able to give us something clear of synthetic data that it tries to emulate and copy, basically. So we're back. As you can see, we had 12 epochs before. Now we used 20. So with more training, you could see it started off kind of blurry. The model started to generate something synthetic. And if you ever see like the image generation pieces, and if you use ChatGPT 4.0, right, how it goes through these iterations of generating a figure as best as it can, that effectively it using the generative adversarial network is to copy an image similar to it, or to generate an image based off of prompt text as best as it can, based off of synthetic information, based off of information that it just makes up. So as you can see here, this is kind of similar to that, of us generating or using creating our own image generation application, right? To generate these pictures and images and synthetic data. Same thing here. So if this information was helpful for you, if you liked what you experienced and what you learned here, please make sure you like, subscribe, make sure you comment, leave feedback, questions. We want to know how we can best serve you and get you the best type of content so that you can learn on your AI engineering or AI development journey. And with that being said, bye-bye.